Hello, and welcome to Chem 1225. Our first lab in this class is the vitamin C titration. And it's a bit of a baptism by fire to show you that Chem 1225 is not like Chem 1215. It's going to be very complicated. You're going to have to take some time to make sure you understand the chemistry. You can't just put a couple of numbers in a simple equation and be done with it. You need to make sure you understand the big picture. So to start with, here is our vitamin C titration reactions that we need to understand. And what I'll do is I'll go over these reactions and the important ratios that we can draw from them, and then I'll explain a couple of little things along the way as we actually perform the reaction. But this here, I've written 3 equations. And I apologize if anyone's colorblind, but I've coded the important chemical species with different colors. So blue here is ascorbic acid or vitamin C. This is the analyte whose concentration we're interested in. I3 minus, this is called triiodide, and triiodide is the titrant. It's what's going to be reacting with our analyte. It is an oxidizing agent, and so it is going to oxidize the ascorbic acid, and in the process it will be reduced. These are the products. The reduced form of triiodide is just iodide, and the reduced form of ascorbic acid or vitamin C is this thing. So you can do redox titrations a number of different ways. You can actually use an electrode to measure the redox potential as you add titrant to analyte, or you can use a color indicator. In this case, we have a starch color indicator that is blue in the presence of triiodide and colorless when triiodide is absent. And so you could imagine doing this titration by taking some ascorbic acid unknown, adding triiodide. It will be consumed in reaction with the ascorbic acid, and then once you reach the end point, maybe the small amount of triiodide that you add in excess would cause the flask to turn blue. And you could do that, but first of all, it's often difficult for your eyes to detect a transition from colorless to slightly colored. It's a lot easier for us to recognize this blue color, I guess, when it's in higher concentration, and we're going to look for it to go from blue to colorless instead. And I don't actually know all the details about why we can't do the reaction in a straightforward way, but there could be kinetic considerations. Perhaps this reaction is slow. There could be there could be side reactions, and we just want this reaction to happen quickly to prevent those side reactions, because a titration is a slow process. Anyway, there are all sorts of sort of technical reasons why you might not be able to do a titration in a straightforward manner like this. And like I said, in this particular reaction, I don't actually know why, but we're going to do what is called a back titration, where we will add an excess amount of triiodide to begin with, and then we will react the triiodide in a secondary reaction in order to titrate away that excess. So here we have a chemical species called thiosulfate, and thiosulfate can also be oxidized by triiodide. And so after we've put in an excess of triiodide, reacted away all of our ascorbic acid, now we're going to do a different sort of titration where the triiodide is in excess down in our flask as an analyte, and the thiosulfate will be in the burette, slowly dripping in to react away that triiodide. And we'll see the flask go from blue to colorless once the triiodide is done being consumed, and that titration will tell us the concentration of triiodide. That will tell us how much of it was consumed in reaction with the ascorbic acid, and that's how we can kind of get at the ascorbic acid concentration in a roundabout way. I like to say that the triiodide becomes a sort of a proxy for the ascorbic acid. Triiodide also is unstable. So if I were to make up a solution of triiodide and leave it on the counter for a day, if I come back the next day, it's going to be all reacted away with the atmosphere. And so it will react with the atmosphere, and it will no longer be the concentration that we expected it to be. Thiosulfate's the same way, by the way. And so we have to deal with both of these problems by generating triiodide right away and using it today instead of getting it from a bottle stored in the stockroom. The way we generate triiodide is with yet another reaction, where iodate, the iodate ion is one that you've perhaps memorized from last semester. Iodate will react with iodide and acid to produce triiodide. As you can see, it's a lot to keep track of. So I color-coded things. The ascorbic acid to the triiodide is a 1:1 ratio. So this will be important to keep track of. Sorry, I'm struggling with too many markers here. Okay, a 1:1 ratio of vitamin C to triiodide. And then thiosulfate is a 2:1 ratio. And so we'll have 2 thiosulfates for every 1 triiodide. And then our iodate to triiodide is a 1 to 3 ratio. Now, what we're ultimately going to be measuring out is an amount of iodate when we generate our triiodide solution, and then we're going to use triiodide in both of these reactions. So what we kind of want is the iodate to thiosulfate ratio and the iodate to vitamin C or ascorbic acid ratio. So what are those ratios? Well, if iodate to triiodide is 1:3, then thiosulfate to triiodide is 2:1. That means that our iodate to thiosulfate, oops, where's my eraser?
Sorry.
Okay. My iodate to thiosulfate is going to be a 1:6 ratio. And the iodate to ascorbic acid is going to be 1:3. One, 2, 3. Okay, there's one more way that I like to present a big picture understanding of these reactions. I like to draw diagrams which represent molar quantities of the different species involved. And I think that at least for some people, like these diagrams can be really useful. So I'm going to go ahead and draw that sort of a diagram. I need to erase a bit of space here, okay? So maybe I'll leave these 2 key reactions up here. We can remember that iodate produces triiodide in a 1:3 ratio, and we'll make that a part of our reaction. Okay. So I'm going to write a little block here that represents our quantity of iodate, and it is going to react to produce triiodide in a 1:3 ratio. So I'll draw this 1, 2, 3 times larger. This is going to make I3 minus. Now that I3 minus is going to react with some unknown quantity of ascorbic acid. And that's in a 1:1 ratio. So I'll just write a big old C for vitamin C. That's the vitamin C. And when this reacts, in that 1:3 ratio, it's going to sort of react away that amount of the I3 minus. And what we'll be left with is this bottom part of the I3 minus. So we intentionally use an excess amount of the triiodide, react it with the vitamin C, and there's some amount of I3 minus which remains. And then we're going to add now thiosulfate using a burette. We're going to add enough thiosulfate that it will stoichiometrically correspond to the amount of triiodide. So this is S2O3 minus. And we know that the amount of triiodide that was in our flask is 1/2 the number of moles of thiosulfate that we added because of the 2:1 ratio, 2 thiosulfates to 1 triiodide. So how is this helpful to us? Well, we know 2 quantities starting out this reaction. We know the amount of thiosulfate because of the burette. This is the thing that we measure in our titration. And we know the amount of iodate because of the analytical balance. We're going to weigh out an amount of sodium iodate in order to generate our triiodide. So if we know the amount of iodate, then we can figure out the amount of triiodide because that's a 1:3 ratio. And if we know the amount of thiosulfate, we can figure out the amount of triiodide left over after the reaction with ascorbic acid, because this is a 2:1 ratio. And so how much vitamin C is there? What is the concentration of vitamin C? Well, these represent molar amounts, so we'll just talk in terms of moles. How many moles of vitamin C are there? Well, it will be this quantity, the total amount of triiodide, minus this quantity, the excess amount of triiodide left over after the reaction. So this we can get from these 2 quantities. Anyway, sorry, this diagram perhaps isn't perfect, but I like representing the molar quantities in this way. And I hope that that's another good visual way to represent it. Now, of course, there's a lot to this lab as far as the procedure. Since you will not be doing the procedure yourselves, I won't tell that to you all ahead of time like I normally would. Instead, I'll just mention why we're doing things as we do them on screen here. And of course, feel free to go back and rewatch this or pause it to understand the diagrams and things. So let's get started on the procedure. Okay, I have my lab assistant Lily with me here today.
Hi.
Our first step is to measure out an amount of potassium iodate. So we've got a piece of whey paper here. I've pinched it at the corners so that it puckers just a little bit. Lily, can you put it on the tray there inside the balance? Right in there. Yep. Turn it around so that it's facing up. Perfect. Okay, close the door. And then we're going to hit the tare button to make it go to 0. And here I have potassium iodate, KiO3. Now this is a very good analytical balance. It's going to give us 4 significant figures. And we need to weigh out about 0.5 grams. So Lily,
What?
can you watch that number and tell me when it reaches 0.5?
Okay. It's past 0.
It's only 0.17.
Oh, yeah. That was 0.17. Now it's 0. 6.
So we can take a little bit away.
It's on 0.6. 0.5. 968.
We'll close that door.
Oh wait. 967.
0.5969. Well, let's let everyone else see that number as well.
Oh, it's kind of going between 69 and 70. Oh, and now it's got 71.
Too much glare. That's better.
Aha. Back down to 70. Yeah, it's kind of going up and down a bit.
Okay. And I haven't measured it to be exactly 0.5 because that's just not necessary.
And it's pretty hot. I bet.
Yeah. Now we've got a 250 milliliter volumetric flask. We're going to dissolve that potassium iodate into this flask, and because we weighed out its dry mass and the volumetric flask tells us the volume precisely, we're going to have a solution of potassium iodate whose concentration we know. So we're going to be very careful here. And fold this whey paper,
So that it looks like a birdie with its wings.
making a bit of a funnel. And we'll get as much of the powder in there as we can. Now, we want to be very quantitative here. That means we want to get all of our amounts as exact as possible. And we certainly haven't gotten all of the powder in there because some of it sticks to the whey paper.
And some of it is molecules that you can't even see.
That's true. So we're going to actually wash the whey paper off into the flask.
What if this told us how many molecules were in there?
It kind of does. It tells you the mass, and we know what's called the molar mass of potassium iodate. So we can calculate the number of molecules.
Oh, that's
Of
cool. I
potassium
bet it's a
iodate.
bunch.
It is going to be a whole bunch. But what the student should calculate is the molarity, or the number of moles. Now, when you're making something in a volumetric flask, you'll want to first add just a little bit of water and dissolve as much as you can in the minimum amount of water. I'm going to go grab a funnel. Okay, so 250 milliliters is a lot, so I'm going to speed things up a little bit with the funnel. We'll add till it's at about half capacity. and then swirl it, and hopefully we'll see that potassium iodate begin to dissolve.
You're making a whirlpool.
Okay, it takes some time. It's almost all dissolved. There's just a little bit left.
Two hours later.
Okay, now a volumetric flask has a mark at some point on the neck. So now we will carefully add water until we reach that mark. So I'll use the funnel for the first bit. Remember, don't be so silly you distract them from the point.
Oh, okay. Is that water or like some kind of fancy clear chemical?
It's just really clean water. Okay, now that I've kind of reached the neck, I'm going to use the spray bottle, little wash bottle, to slowly add water until we reach the mark.
Stop. That would be like a 20th of an inch higher than the mark.
As with all volumetric glassware, there will be some curvature here. We call that the meniscus. And you want the bottom edge of that curvature to just kiss the mark. And I don't know how well you can see that, but I feel like I've done a pretty good job of that. Secured the cap and make sure that it's well mixed by inverting it several times. And now we have a standard potassium iodate solution that we can use for the rest of this lab.
That looks really cool. I like how when it's upside down, it goes up fast, but when it's right side up, the air comes in slow.
Okay, so now we're going to be standardizing our sodium thiosulfate solution. I have here some thiosulfate, which is about 0.1 molar, but thiosulfate is a redox active chemical, and so over time it will react, and we don't really know its true concentration. So before we can use the thiosulfate in our titration with the citric acid, we're going to have to standardize it or find out its true concentration. So here we have a burette. I know you didn't use these much in 12-15, but you should be at least a little bit familiar with them. I'm going to fill it up from the top. And I'm going to go a little bit beyond the 0 mark. Now the burette has markings all along it. It starts 0 up at the top. I'm not sure if you can see that or not.
It's kind of fuzzy.
Yeah. Lily's saying that it's fuzzy. But anyway, it starts 0 at the top and then goes down to 50 at the bottom. And this tip here is filled with either air or whatever solution was used last. So I'm going to go ahead and open that up. I bop it to get rid of some bubbles. And now we're ready to go. It's actually dropped quite a bit below 0 now, so I think I'll add just a little bit more. But there's no need to start at exactly 0. You can start it wherever you like as long as you note the starting point. Now I've gone beyond 0, so I guess I'll let out a little bit more. There we go. Perfect. So we just need to note the starting point and note the ending point, and the difference between those two numbers is the volume delivered. So I'm going to read from the bottom of the meniscus, and we have markings at every 1/10 of a milliliter. We can estimate the position between those markings, so we get numbers to the 100th of a milliliter, which is going to give us about 4 sig figs total for the volume delivered in the course of this titration. So I'm reading really about 0.31. 0.31 is our starting position. Now, here I've got an empty Erlenmeyer flask, and this is where we're going to put our potassium iodate solution. But remember, we don't really want to titrate potassium iodate. We need triiodide. And so we're going to first get about 25 milliliters of potassium iodate, is what your manual says. I actually found a 20 milliliter pipette instead. I couldn't find a 25, but this will deliver 20 milliliters. So we'll
Do you also have a 5 one? Because that would work.
Yeah, but
Using both of them?
it's better to just do it in one go.
Okay.
Okay, now pipettes, I believe you did use, so I won't explain too much of what's going on here. But we're gonna
That looks fun.
draw up. Okay. And now I'm gonna let the water come down to the mark. And again, we want to be as careful as we can be. So I will now deliver the 20 milliliters of potassium iodate solution into this Erlenmeyer flask. And I'll touch off the tip, because that drop on the tip should count as delivered. Now this is just the potassium iodate, so in order to turn it into triiodide, we're going to need two things. We're going to need 5 milliliters of a half molar sulfuric acid. This does not need to be measured precisely, so I'm just using a graduated cylinder, and I'm not even being very careful with the cylinder. That's about 5 milliliters. And about 1 gram of solid potassium iodide, Ki. And again, I'm not being very careful with this. That is an excess amount. I'm not even going to measure it because I know about how much 1 gram is. Although there's a big chunk in here.
Oh, that happens with brown sugar at times.
Yeah, just like with brown sugar, huh? Tell you what, maybe I will go measure it. I'll just be back in a sec. Okay, here I have about 1 gram of potassium iodide. I'll add that. And you'll notice it immediately begins to change color. And then lastly, we're going to add just a touch of sodium bicarbonate. Now we added sulfuric acid. We're adding about 1/10 of a gram of sodium bicarbonate. And what that will do is generate carbon dioxide. A small amount of carbon dioxide will be generated and create a blanket of chemically inert carbon dioxide so that the oxygen of the atmosphere can't react with our triiodide now that we've generated it in solution. Now, we're going to begin the titration. So, and you're asked to make observations. So this is the color of the flask now. It's a brown, and we could add the starch color indicator right away, but it's actually helpful to first do the titration until we go from a brown color to a yellow color.
Brown, yellow, brown, gold-ish. Actually, that looks kind of like amber.
It's an amber color now.
Yeah. Oh, it's starting to look red. That's cool. Color changes a lot.
Yeah, isn't that fun?
Yeah. Now it's a lighter amber.
I'm going to swirl it, and I'd say it's approaching a dark yellow. So
A light orange.
now is the time to add the starch indicator. Hopefully a couple of drops here will turn this blue.
It looks kind of black.
Yep. We'll swirl it around. Get it well
Now it's
mixed.
green. Dirty green.
And now we can finish off the titration. And we're going to want to be very careful as we approach the end of this titration. When that blue color is going away, let's add a little bit more starch.
What about real cornstarch? Isn't this just a starch activator?
This is cornstarch. I made it while you were eating lunch.
Oh.
Yeah, we actually paused the video, went and bought some cornstarch because I didn't realize we were out of starch indicator.
Now it's kind of green. It's getting much closer. But will it be blue? I don't think so.
Ooh, and did I overshoot it? Okay. Well, that's fine. So I overshot it. But that means that we can be really careful with the next one. We'll take a look at how many milliliters that was. Looks like it was about 15 milliliters. And we'll do another one where we have some foresight and we can approach 15 milliliters a little bit more cautiously. In fact, I'm not even going to refill this because we've got plenty of room to go. I'm just going to rinse out our flask and we'll do another trial right away.
Well, usually in my school, when we get something wrong, teacher's just like, well, this should happen. Sorry, we are out of materials.
No, we're going to actually make this work, and we're going to do 3 trials of it. Okay, so it looks like we are starting at 16 point, call it 16.0, just right on the nose. And we're going to add about 15 milliliters, so we'll stop at about 28 maybe, and add slowly from there on. Okay, now we got the nice dark blue color.
Ish. It's kind of green.
It's true.
Deep green.
And I'm going to add it literally one drop at a time from here on out.
That sounds kind of annoying.
It's a bit slow going, isn't it?
I know. Hi.
And there we are, colorless solution. So this looks like .26 milliliters. And we'll just do this all 2 more times. Okay, so we'll try this again. Looks like our starting level is at about 0.30 milliliters. Less than a milliliter, 0.30 milliliters. We'll go to 12 milliliters quickly, and then we'll add the starch indicator and go dropwise from there. So this is at 13.38 milliliters, 13.38. There are some flecks in here. That's because my starch indicator is cloudy. I could have filtered it. Instead, I just tried to grab the supernatant. But I'm going to add one more drop just in case that makes a difference. And actually, I'm going to say it did. I called it maybe a bit too soon. Should really be 13.41. 13.41. Okay, we're starting at 0.36. 0.36. Okay, there it is. That's 13.50 milliliters. 13.50 is the ending point. Okay, so the point of all of those titrations was to find our thiosulfate concentration. Now, with the calculations, those three trials, average them together, and you'll know now the concentration of thiosulfate in the burette. And now it's time to actually do the back titration of a sample with vitamin C. So we're going to do orange juice here. And I'm suddenly realizing I perhaps should have chosen some other juice that doesn't have quite as strong of a color, but I think we'll manage. We'll see. This orange juice, if we look at the label here, 240 milliliters is the serving size, and 240 milliliters is supposed to have 80 milligrams of vitamin C. And so we can use those numbers to figure out what the manufacturer of this orange juice believes to be the concentration of vitamin C. Now we're going to actually perform the titration and see how close they are. So we'll start by taking 50 milliliters of the orange juice, which is quite a lot. And we'll put 50 milliliters of orange juice in our flask. And then we're going to add quite a lot of sulfuric acid this time, 40 milliliters. And this doesn't have to be quite exact, so I'm just going to be maybe a little bit sloppy here. 40 milliliters of sulfuric acid. And about a half a gram of sodium bicarbonate, which will be about that much. That gives us the blanket of carbon dioxide. We're about to have a bit of a volcano situation here. Narrowly avoided. Okay, then we're going to add 20 milliliters of our ascorbic acid. Again, your manual says 25. I found a 20 milliliter pipette, and so you know, the principle is the same. You'll just want to use the correct number. This is the potassium iodate solution, 20 milliliters. Okay. And then about 1 gram of solid potassium iodide. This is the Ki. And that's about 1 gram. Because this reagent is in excess, we don't need to be terribly precise about it. And my Erlenmeyer flask is already pretty full. We need to be able to stir it and swirl it, so I'll be right back with a bigger flask. We'll transfer this over and we'll use the bigger flask from now on. Okay, I should have used a bigger flask from the start, but I think we can transfer this and it won't all be a loss. And we do want to make sure we get everything, so rinse this out. And collect our rinsings. Let's just do one more for good measure. Okay. Looks pretty nasty. So as before, we'll titrate it without the starch indicator at first, and then we'll add starch later. Looks like this starting point is 0.54 milliliters. There we go. And I believe we're seeing the brownish color go away. There's still going to be a little bit of orange from the orange juice itself. I'm going to add a little bit more starch indicator than normal because I want it to be nice and dark. And I think we'll go dropwise from here. We really have no idea how much we're going to need. So 12.65. Okay, we're starting at 0.50, right on the nose. 12.63, 12.62. 12.62. Okay, so using orange juice made it pretty difficult to tell the color change. I'll be interested to see how these numbers work out. It certainly wasn't impossible to tell that there was some blue in there and to watch for the blue going away. But anyway, so that is how you do the back titration of vitamin C.